So talking about other non-electrical techniques, so we have looked at electromagnetic radiation, we have looked at sound. Now we will look at temperature. When there is partial discharge happening, PD radiates heat, and therefore they should be detectable by thermography. So if I have a thermal imaging camera, it should be able to detect the presence of intrinsically hotter regions, and those particular hotter regions must be the location of the PD. But the problem with this is that it does not work for enclosed structures. But we do have daylight corona camera. In this daylight corona camera, you have independent ultraviolet video. You have a camera which captures independently the ultraviolet the video in ultraviolet light. The advantage of ultraviolet light, it gives a weaker picture, but it gives a more high contrast image. And at the same time, you have a visible camera. The visible camera will give you a clearer picture. So when you take the two images together and combine them together, they may be able to give you a good indication of the PD location. But thermography has limited uses. Next, we come to chemical energy or chemical changes brought about by partial discharges, which can be used for a detection of PD. And the most important, and in fact, this is a very cheap method, and it is the most commonly used PD detection method for transformers, and that is the DGA or the dissolved gas analysis technique. In this, let's take the transformer oil. The transformer oil, when there is a PD happening inside the transformer oil, there is heat generated, there is energy generated, and as a consequence of this, certain reactions might take place. And those reactions can cause the production of new materials. So byproducts will be obtained. Byproducts will now mix with the original gases or original liquids. When you have the transformer, on top of the transformer, you have the headspace, and gases accumulate in this region. So it is possible to extract some amount of the gas from this headspace and do an analysis of the gas constituents. And we might find that if there is a partial discharge has taken place, there might be certain byproducts which were not there to start with, or in the ratios that the ratios of those byproducts or the amount of those byproducts might change. Or you might even analyze the oil and find the constituents of the oil. So the measurement of the byproducts is what gives you an idea about the PD activity. You do this in hydrogen-cooled generators, gas-insulated substations, but primarily this is done in transformers where you have oil-filled equipment. The quantity and the mix of gases depends upon the nature of the fault as well as the severity of the fault. This is a very cheap method for screening faults. Let us see how this works. The sample is obtained, as I said, it might be obtained from the gas phase, or it might be obtained from the oil volume. There are various gas extraction techniques that can be used. For example, you use a tubular pump for vacuum extraction, or partial degassing, direct injection, headspace analysis. So these are various techniques in which the gas is extracted, and then this gas is measured for its constituents using gas chromatographs or infrared spectrometers, semiconductor sensors, miniature fuel cells. In fact, portable gas chromatographs are also available these days. So you can do actual field measurements with commercially available fault gas detectors. There are selective gas permeable membranes, which allow certain gases to pass through. So you take that gas combination mixture of gases and using a portable FTIR spectrometer or a portable gas chromatograph to analyze the constituent materials. Let us have a look at what are the kind of strategies that are used for using dissolved gas analysis to interpret partial discharge or other faults taking place inside a transformer or other equipment. Remember, here we are essentially looking at gas ratios. We are not looking at the absolute levels of dissolved gases. We are looking at the gas ratios. So, for example, there can be various ratios that we might be interested in. For example, the ratio of CH4 to H2. And what we do is, depending upon the range in which that value lies, we can assign a code. So if the CH4H2 ratio is less than equal to 0.1, code 5. If it lies between 0.1 and 1, code 0. If it lies greater than 3, code 2, and so on and so forth. So we look at CH4 by H2, we look at C2H6 to CH4 ratio, C2H4 to C2H6 ratio, C2H2 to C2H4 ratio. So these are the 4 ratios, and depending upon the values of this ratio, we assign several codes. And then let us look at all these combination of the 4 codes. So we have 4 gas ratios and 4 codes associated with every gas mixture. So let's say you have a situation where all the codes are 0, 0, 0, 0 for all the ratios 0, 0, 0, 0, which means that the CH4H2 ratio lies between 0.1 and 1. C2H6 to CH4 ratio is less than 1, C2H4, C2H6 is less than 0, and C2H2 to C2H4 is less than 0.5. When you have this combination, you have a gas ratio combination of 0, code combination of 0, 0, 0, 0. This 0, 0, 0, 0 combination corresponds to normal situation. So as long as the oil is normal, you will continue to get this code. Now let us imagine that we continue to get 0 for all the ratios except for the first one, where we get code 5, where this ratio falls to values less than 0.1. This indicates that partial discharge must be taking place. Whereas with a configuration of 0, 0, 0, 1, where these 3 ratios are within the normal range, only the C2H2, C2H4 ratio has a code of 1, which means the range is between 0.5 to 3. It should be less than 0.5, but it is above 0.5, but less than 3. This is indicative of flashover. There has been a flashover which has stopped. There is no power follow through. So we can, in this combination, using this various combinations of these 4 ratios, there are several different kinds of faults that we can identify. Partial discharge, slight overheating, less than 150, overheating up to 200, overheating up to 300, general conductor overheating, winding circulating currents, core and tank circulating currents, flashover, arc, continuous sparking, partial discharge with tracking. When there is oil and there is an insulation, there is a large likelihood of tracking happening on the surface, higher than normal temperature in insulation. So depending on what kind of a fault you have, you may need to take corrective action. This table that we have here is called the Rogers fault gas ratios. It is based on Joseph B. DiGiorgio's dissolved gas analysis of mineral oil insulating fluids, and this is called the Rogers gas ratio. There are several such tables, standards. One is the Rogers ratio, the other is the Duval's triangle. It's again a similar situation. You have a triangle which comes from Duval, IEC 60599, 1999 Duval's triangle edition. This is what it is. You have the 3 axes, and each axis corresponds to the percentage of a particular gas. So on the x-axis, you have C2H2, C2H4, and here you have CH4. So along the 3 axes, you have the ratio, the percentages of 3 gases. And depending upon the contents of these 3 gases, you can locate a gas sample anywhere within this triangle. Now, as you can see, this triangle is divided up into various regions: D1, D2, D plus T, T3, T2, T1. What are these regions? Right at the top near this vertex is the PD, which corresponds to 98% CH4. We have CH4 along this axis, and when you have above 98% CH4, that corresponds to PD. So that is, any PD would be located in this particular region. Other than that, you have T1, which is 4% C2H2, 10% C2H4, and so on and so forth. And depending upon which region you are located, you can identify the fault. PD, of course, corresponds to partial discharge. D1 corresponds to discharges of low energy. D2 corresponds to discharges of high energy. T1 is a thermal fault with temperatures less than 300 degrees centigrade. T2 thermal faults between 300 to 700 degrees centigrade, and T3 thermal fault greater than 700 degrees centigrade. So depending upon what you're looking at, the kind of oil, the kind of faults you're trying to identify, any of these methods can be applicable. Now, the question is that, so we have talked of various kinds of electrical as well as non-electrical techniques. In the context of various equipment, we have discussed transformers because I wanted to discuss an equipment which is not as complex as rotating machine, but it is not as simple as a gas insulated substation either, because transformer has a mix of complexities. But then the question is, which is the PD measurement technique that you use, that you would like to use among all these many techniques that are available? The selection of the PD measurement technique depends on many factors. One thing that we have to keep in mind is there are certain techniques which are better suited to certain equipment, certain scenarios, and then most of the time, one of the techniques, just using the use of one technique is not going to be sufficient for you to be able to locate and detect with confidence, with any degree of confidence, the fault in a equipment. So here I have a table of the type of plant and the PD measurement technique that is best suited to such equipment. For example, for generators, you would use an electrical technique, tan delta. I've not talked about tan delta. We will talk about tan delta measurements later when we discuss various measurement techniques. But then the tan delta measurement, which is a loss measurement technique, can also be indicative of PD happening in the equipment. For cities, you can use the capacitive technique, you can use the antenna technique in a generator. Whereas for a circuit breaker, you might use the electrical technique, the capacitive prep technique, and the acoustic technique. As you can see, transformers, many of these are suitable. You use electrical techniques, capacitive probe, antenna, acoustic, chemical. Chemical is the most commonly used. For bushings, you might use tan delta. So this is where tan delta becomes useful. Tan delta or antenna or chemical technique might be used. So depending upon the kind of, so for overhead bus bars or insulators, the best technique to use is of course thermography, because it is open air and we have access to, the daylight camera can actually capture images. So depending upon the kind of equipment you are looking at, you will choose your measurement technique, and the balance among the costs of a plant failure. For example, how costly is a fault going to be? And how costly is it going to be to monitor health throughout the life of the equipment? What is the repair cost? What is the outage loss due to outages? And what is the cost of implementing condition monitoring techniques? All these have to be taken into account. You spend a lot of money in building online condition monitoring system, and then you find that the quality of information is not very good, it's not useful. So the decision would be unique to the situation, which technique to use, whether to use online or offline condition monitoring technique, whether you're going to use a combination of several factors. All this will be decided by not only the situation in hand, but also the economics of the situation, and the decision will be unique to the. So let us take a few instances and see how it works. One of the situations that I want to talk about is cable mapping. Now, so far we have really been talking about detection. I have mentioned location, but we have not really discussed why location is important. Cable mapping is an important example because when you have underground cables and you know that there is a fault somewhere in the cable, it is not enough to know that. You need to know at least which section of the cable is faulty so that you can take action. And therefore, location of the PD is very important in case of cables. So without location, refurbishment of a plant item hidden underground and extending potentially over many kilometers would be extremely daunting. And therefore, we have this cable mapping technique, which is very extensively used. You have the cable, and the cable is disconnected at both ends. One end of the cable is open circuited, and the other end is going to be used for measurements. We connect an external high voltage AC supply at the measuring end. Now, because we want the supply to be portable, it is better to have a low frequency supply. The portability of the supply requires the frequency of the supply to be between 0.01 to 0.1 Hertz. And when we do that, when we supply this, energize this, there would be a signal. Here we have a C and we have a Z in series. Across the Z, we tap out the signal and this signal goes to the detector. Now, when a signal from the is sent into the cable and reaches the discharge, so you have the discharge side, and from the discharge side, a signal travels to both ends of the cable. Now, if your detector is on this side and this side is open circuited, there will be a direct signal which will be reaching the detector directly. It will take much less time because it will travel directly. It has lesser distance to travel. On the other hand, there will be another signal which will be traveling to the other end of the cable, to the open circuited end, where it will be reflected back, and it will travel back and travel this entire distance back to the detector here. The detector here is, of course, your CZ combination. So now the situation is this, that you have two signals. So you will register two signals. The first signal will have a high magnitude. This is the signal which travels directly to the detector. And there will be, at some time later, at delta T2, a smaller signal, lower magnitude, which is definitely the reflected signal. So when you combine the information of the time lapse between the direct signal and the reflected signal, knowing the velocity of the waves, this will give you a way of estimating the location of the discharge site in between these two open ends. So part of the discharge pulse propagates towards the detector and part to the open circuit. Two pulses arrive due to one discharge. Relative time of arrivals for the cable as a whole must be known. How would we know that? We need to know the velocity of travel of the reflected signal as well as the direct signal. Only then we can convert the time difference between the two signals to a spatial difference. So for that, what we have to do is we have to first use a calibration pulse. We inject a calibration pulse at the detector end and detect its time of arrival back to the point from the OC end. So in this case, what you would have is you will not have a discharging site. You will have a single signal, and you know the position of the signal. The position of the signal is at the detector end. So you will obtain only one signal back. You will detect only a single signal due to this calibration pulse. And when will that be? It will have traveled twice the distance of the cable. It will have traveled to the open circuit end. It will be reflected from the open circuit end and will travel back. So it will traverse twice the distance of the cable. What we will do is we will estimate the time of the taken for the signal to travel twice this distance. So the time of arrival back to the point from the open circuit end will be estimated. Percentage location of the degradation sites along the cable can be ascertained now because we know the length of the cable and we know the velocity of propagation. Percentage location of PD along cable will be given approximately as 1 minus del T1 minus del T2, the difference in times between the two signals, divided by the delta T for the cable, the time required for the signal, the calibration pulse, to traverse the entire cable distance. And as a percentage of that, so the time percentage or the time ratio will give a measure of the distance ratio. Map of cable produced with cable length on horizontal axis and discharge magnitude on vertical axis is seen here. And from this, what you can figure out is you can figure out the size of the degradation site as well as the location in the cable. The nature of the degradation, what kind of degradation? So you know the size, whether it's a huge thing, and the location. What kind of problem do you have? What is causing the partial discharge? What is happening at the site? The nature of the fault. For that, you will have to use the associated phi-QN plot. So therefore, in order to get full information so that you can act upon it, it is not sufficient to have one technique. You'll have to combine several techniques together depending upon the problem in hand, and only then you will be able to take corrective action. So from the cable mapping technique that I have just described, you get the size of this discharge site, You also get an estimate of the location of the discharge site. But the nature of the degradation has to be obtained from the conventional phi-QN plot. The phi-QN plot will only come from the IEC measurements. So IPD measurements, that is the conventional electrical PD measurement technique will give you the phi-QN plot. So you cannot do away with the conventional technique. In this context, just as we have talked about transformers, it is also interesting to talk about gas-insulated substations, because gas-insulated substations, as I said, is a substation which is completely enclosed and we do not have access to it. And if there are any faults, we need to, it's a quite costly thing to have to deal with any faults. They are more reliable, they don't have so many faults in the first place, but when they do, they can be problematic. So we have to know what are the and partial discharge monitoring of gas-insulated substation is one of the principal techniques for condition monitoring of gas-insulated lines or gas-insulated substations. So if we are going to monitor PD, what are the PD-inducing defects that you would expect in a gas-insulated substation? Moving particles. Inside the gas-insulated line, inside the tank, there might be particles, loose free particles. And when you apply an electric field, these particles will be levitated. They will move in the direction of the field. They will move up and down. If you have an AC signal, they will continuously hop on the surface of the conductor of the tank. You will have also, because of gas flow, there might be moving particles. There might be electrode protrusions. So moving particles, when they move into the region of high field, they will cause PD. There might be electrode protrusions in the first place. And because of field intensification near the electrode protrusions, partial discharge may take place. There might be fixed particles on the insulating surface, and these may cause local field enhancement, giving rise to PD. There may be loose non-floating electrodes. Non-floating electrodes, the potential is non-floating. So these loose electrodes may acquire high voltages and cause discharges. There may be voids in the solid insulation of the spacers. This is the most difficult to trace because it is happening inside the GS, inside the solid, a small discharge is taking place, and we need to be able to estimate that. The most common techniques used in gas-insulated substations are acoustic detection techniques and ultra-high frequency techniques, where you use, instead of acoustic sensors, you use ultra-high frequency sensors to to detect the ultra-high frequency radiation. But whenever I talk about these things, remember, in the first place, some electrical detection is probably already in place, and these are additional techniques that are used. I'm not going to talk anymore about the different kinds of techniques, but we have talked about, we see that no matter what technique we use, we are never rid of the conventional PD detection technique. And in that context, I want to talk about PD signature analysis. Right at the outset, we have talked about the fact that the phi-QN plots that we obtain from different kinds of defects have their corresponding signature. And I would like to talk about that. PD signature analysis. Let's say this is the ellipse. As I said, the ellipse is actually the sine wave folded onto itself. If you have a pattern like this is a very typical pattern, and anybody doing any kind of PD measurement in the lab would be familiar with this pattern. This is, in an elliptical display, it is necessary to locate the voltage peaks or zero positions on this trace. So what we do is we first figure out which are the zero markers. These are the points at which the sinusoidal wave reaches zero. And this is the positive wave and this is the negative wave. So we can use some electronic detectors to use the zero markers, and then we can figure out whether the discharges are happening near the peak, in one cycle, or in both positive and negative cycle. Are they kind of congregated together? This picture, this is a typical discharge from a sharp point in air at 5% above inception voltage. I've talked about corona inception voltage. Once the corona incepts, it will increase in number. The number of pulses will increase before magnitude increase takes place. This, as I said, this is a image, this is a signature that is familiar to everybody almost, because this is typical of corona in air, where you can see this is taking place somewhere close to the peak, in and around the peak, and there are a large number of PD pulses clustered together. Then you can have solid dielectric bound cavity. You have a cavity, and far away from either of the metal electrodes, you have a cavity which is encapsulated. This is typical of voids found in solid sheet material and subcast components. We use epoxy resin a lot in high voltage insulation, and this is the kind of void that epoxy resin will definitely have. As you can see, this gives rise to a signature like this. The discharges occur in advance of the voltage peaks on both the positive and the negative half cycles, and they have more or less the same amplitude on both sides of the ellipse. They have the same amplitudes and same numbers, but on both sides of the ellipse, you have the same amplitude of cycles and pulses, same amplitude pulses. So you will have as many pulses as on either side. However, differences of 3:1 in magnitude from one side of the display to the other are normal. So they may be equal, as can be seen here, or you may have a difference to the extent of 3:1, but the number of pulses are more or less the same. Okay, this is about the phi QN analysis. So you look at the phi QN analysis and you have an inkling that this could be a void somewhere, dielectric bound cavity. Then you look at other factors. You find that the discharge extinction voltage is equal or slightly below the discharge inception voltage. And the time of voltage application usually has little effect on the discharge pattern displays during a single test. So when you see these three things together, you have a you have enough reason to believe that this would be due to a dielectric cavity, a dielectric bound cavity. But then if you have something like this is very drastically different from the previous signature. Here what you have is, you have discharges in advance of the voltage peaks, and these are asymmetrical. They are in the ratio of 10:1. They're nowhere close, not even like 3:1. They are very different, at least in the ratio of 10:1. Also, you see that there are a smaller number of large discharges in the negative peak, and there are a larger number of discharges on the positive peak. When you see this pattern, this is immediately you know that this is not matching with the pattern that we have just encountered, and this is typical of a pattern where you have a cavity which is close to one metal. So on one side the cavity has metal, and on the other side it has dielectric. So it must be due to some kind of delamination between the electrodes and the dielectric material. If you have a small number of large discharges at the negative peak, it means that the void is usually located where the metal is at ground potential and the other phase is the dielectric. If this pattern is reversed, the indication is that the metal is at the high potential. So here you have the negative peak scenario. Then you have case 3, where you have an air gap between a metallic conductor, such as a loose connection to a shield or a screen. This is what you have. Or you might have a gap between two independent metal objects across which a voltage is produced by electrostatic induction from the test circuit, such as if you have an ungrounded metallic objects and potentials are induced and they're not earth, so there will be a potential difference, and that potential difference might be high enough to cause breakdown. If that is the situation, then this is the phi QN pattern that you will be seeing. There will be discharges of the same magnitude and number in both half cycles, and they will all happen in advance of the peak. The peaks are marked here. Before you reach the peak, you start to, before you reach the peak, you start to see the discharges, and the discharges are more or less of the same magnitude and same numbers on both half cycles. As you increase the voltage, the pulses cover a greater portion of the waveform. This is about the phi QN pattern. Then you look at the ratio of the extinction voltage and the inception voltage, and in this case you will see that the extinction voltage coincides with the inception voltage, and the response is unaffected by the time of application of the test voltage. That gives you an idea that this is an air gap which is a fixed dimension which is breaking down. Case 4, you have discharges which are located symmetrically about both voltage peaks. The locations are erratic, the magnitude is erratic, the inception voltage is variable. Extinction voltage is lower than inception voltage, but the inception voltage is not fixed. It is varying quite a bit. Also, so you don't have a clue about what is happening. And then you see that the observed magnitude increases rapidly with voltage, and larger and unrepeatable changes in magnitude may occur particularly at higher voltages. So these are indicative of carbon tracks or dielectrics inside the material. So as you see, I have just given you some examples. The point is that the various kinds of defects within a solid insulation will give you typical patterns. And the patterns will give you an indication of what kind of defect it might be. But remember, here we are talking about a single discharge. If you have several discharges of the same kind or several discharges of different kind, the signals will superimpose on each other and you will not be able to get a pattern. So it is not an easy task. And the main thing that is to be said about partial discharge detection is that we have the measurement techniques. What we do not have are foolproof interpretation strategies. And therefore, what we are still need to do is we need familiarity with the patterns for every kind of fault so that we can correlate them when that happens. So PD detection techniques generally take the help of expert systems. What are expert systems? It is a class of artificial intelligence which is restricted, in this case it is restricted to determining the type of PD deterioration mechanism occurring rather than distinguishing PD from noise. So we would like to figure out, is there PD happening, and if it is happening, what kind of PD is happening? We're not really looking at a quantitative analysis. PD patterns based on the, so how do we do that? We look at the PD pattern and we analyze. I'm talking about the simplest case of PD analysis here. We look at the PD pattern and we look at the ratio of the positive to negative pulse magnitude. We look at the trends over time. I've mentioned this earlier. So for example, if you see that there is a lot of erratic PD activity, PD extinction voltage is lower, PD inception voltage is varying, there is no match, there is no correlation between the number of pulses in the positive and negative half cycles, you already begin to think that it must be treeing. But you know it is treeing when you see there is a large activity which is followed by a large duration of quiescence when nothing happens. And then again the PD activity starts. That is typical of treeing. So PD patterns based on all these techniques, ratio of positive to negative pulse magnitudes, trending over time, trends with machine load, etc. are analyzed. And then after you have all this information, apply tools like neural networks or wavelets to PD pattern recognition. You might want to do even continuous online monitoring so that you can see whenever there is a change in the trend, you know something is wrong. To conclude, PD studies therefore have twofold importance. They enable the development of new insulating system if you know what causes PD, if you know what are the PD stresses and how PD stresses can cause degradation of your system, you can prevent it. So therefore, PD studies can enable the development of new insulating systems which are resistant to PD stressing. In fact, we will discuss in a later lecture how certain materials can be designed to be resistant to PD, to train or PD erosion due to PD. We can also use this to determine the life of the system, to predict the remnant life for existing plant systems. So therefore, as I have been saying, we can never stress we can never stress too much the fact that PD studies are of utmost importance in obtaining better designs and in better plant management, life management. What are the most important challenges then? We've been talking about what works and what doesn't work. The most important challenges is in understanding how PD causes degradation, because it's very difficult to study PD and the various pathways are almost impossible to follow. So understanding how PD causes degradation and which are the key parameters of measurement still remains a challenge. The ability to make measurements under adverse conditions. We can make measurements, but how to improve the signal to noise ratio so that we can make meaningful analysis of that. So these are some of the references that I have used in my partial discharge lecture. This is a famous book by Bartnikas, and then you have partial measurement and interpretation. This is an article by Natras in the IEEE Electrical Insulation magazine, which has a lot of on-field articles on on-field studies. And then this is, of course, Haddad, which we have been using as a textbook.